Welcome to this explainer. Picture this. You've just poured years of your life and literally millions of dollars into engineering a stunning state-of-the-art bipedal robot. Now you gotta teach it how to walk. But here is the really visceral, high-stakes problem we run into. Training a real-world biped takes millions of attempts. If it falls over even once during that super fragile learning process, crack. That's millions of dollars and years of research totally shattered on the lab floor. You simply cannot rely on physical trial and error when the errors literally destroy your robot.
Which brings us to a pretty terrifying reality. Doing this training in the physical world is brutally slow, it's inherently dangerous, and yeah, it is incredibly expensive. So, the obvious solution, you move it to a simulator. Inside a sim, you've got this perfectly sterile environment with unlimited resets. It's completely deterministic, you can run thousands of tests in parallel, and most importantly, it's 100% safe. Zero physical damage whatsoever. But as we're going to see, taking a digital brain from a perfect simulation and dropping it into a messy physical machine, well, it's actually one of the hardest challenges in modern engineering.
To understand exactly how engineers pull this off, we're going to break this massive sim-to-real problem down into 5 digestible chapters. 1. Meet the reality gap. 2. The sim-to-real toolkit. 3. The teacher-student secret. 4. The 2026 master recipe. And 5. Pitfalls and real-world scale.
Chapter 1. Meet the reality gap, the central antagonist of robotics.
Okay, let's dive right into this. Why can't we just drag and drop a highly trained digital brain right into a physical machine? Well, the answer is what engineers call the reality gap. Essentially, this is the systematic difference between what happens in your simulator and what actually happens in the real world. Simulators are, by nature, kind of wrong. They're sterile. So a robot brain trained in a sterile simulator gets totally sabotaged by unmodeled physics. The real world is full of messy things: wind, dust, variable lighting. Bearings have way more friction than a neat mathematical equation assumes. Even cameras have tiny lens distortions that the simulator just completely misses.
And to put that gap into perspective, get this. 99% of simulation models skip the really crucial physical nuances. They completely ignore things like tiny motor delays, mechanical backlash, or motor saturation. So if you train your robot in that 99% flawed simulation, it hasn't actually learned how to walk. Nope, it's just memorized the simulator. The literal second it steps into the physical world, it fails.
Chapter 2. The Sim-to-Real Toolkit, our foundational weapons.
Now, what's really interesting here is how we fight back against this gap. Historically, engineers have used 2 entirely different philosophies: guessing versus measuring. The first tool is domain randomization, or DR. The idea here is to just randomly guess and vary every single simulator parameter. You randomize the mass, the friction, camera positions, sensor noise, the whole shebang. You're forcing the robot to generalize so it can handle basically anything. The upside? You don't need any real-world data at all. One recipe works for lots of robots. But the downside is, if you over-randomize, your robot gets paralyzed. It becomes overly cautious. On the flip side, we have system identification, or SI. This is the philosophy of measuring. You take super precise physical measurements of your actual robot, like exactly how much friction is in a specific arm joint, and you plug those exact numbers right into the sim. The upside is a really precise, low-noise training target. The downside? Even the tiniest unidentified effect, like a microscopic motor deadband, is totally invisible to the robot and will still cause it to crash the moment it's deployed.
Because neither guessing nor measuring is totally perfect on its own, we have a third tool, domain adaptation. You train the robot in the simulator, but then you fine-tune it with just a tiny bit of real-world data. It closes that final gap. It's kind of like letting a driver practice in a racing video game for months and then letting them take just a few real laps around the actual track so they can feel the real steering wheel.
Chapter 3. The Teacher-Student Secret, Distilling Privileged Knowledge.
So the crucial point is how this dynamic actually works, because it absolutely revolutionized legged robots. In the simulator, you first train a teacher policy, and because it's in a sim, the teacher basically gets cheat codes. We call this privileged information. It knows the absolute ground truth about everything: exact friction, perfect terrain height, IMU drift, you name it. It learns to walk flawlessly using this God mode data. Then you bring in the student policy. Now the student is completely blind to those cheat codes. It only gets to see what the physical robot's actual sensors will see out in the wild. But through a process called distillation, the student learns to infer all those privileged cheat codes just by analyzing the history of its real sensor observations. It basically figures out how to mimic the teacher's perfect movements without ever actually seeing the teacher's perfect data. It is brilliant. And this brilliantly illustrates the sheer scale of how we do this today. We use massively parallel simulators like Isaac Lab or Mujoko MJX. We're not training just one robot at a time. No way. We are running 4,096 parallel humanoids on a single GPU simultaneously. Because of this massive scale, the system gathers literally years of physical experience in just a matter of hours. The reality gap shrinks drastically because the training data is so incredibly wide, making domain randomization practically free.
Chapter 4. The 2026 Master Recipe, Synthesizing the Ultimate Workflow.
Let's move to and see how this all builds into the definitive modern workflow for training a robust robot. Step 1. You spin up a massively parallel sim, throwing domain randomization at gravity, friction, and motors across thousands of virtual worlds. Step 2. You train that privileged teacher using all that sweet ground truth data. Step 3. Distill that knowledge down to the student policy, strictly limiting it to realistic sensor data like leg joint encoders. Step 4. You optionally apply observation adaptation to map real-world sensor noise. And finally, Step 5. You deploy it zero-shot to the physical hardware. If it acts a little wobbly, you just do a few minutes of real-world fine-tuning inside a very strict, safe boundary so you don't break the machine.
Chapter 5. Pitfalls and Real-World Scale, where it breaks and shines.
Okay, so it sounds like magic, right? Well, let's be real. It isn't completely foolproof. Here are the rapid-fire pitfalls that literally keep roboticists up at night. First, if you randomize your simulator too much, like if you tell it the floor might be made of pure ice or superglue, the robot gets so terrified it won't even take an optimal step. But too little randomization, and it can't handle the real world at all. You gotta match the expected real-world vibe. Third, misidentified parameter spaces. If you waste time randomizing the camera color when the actual physical problem is a motor delay, your robot is still gonna fail. Fourth, privileged info leakage. If the teacher uses a shortcut that the student physically cannot sense, the student will just never catch up. And lastly, absolutely crucial, lacking a low-level safety shield. Even a genius robot brain needs basic, hard-coded speed and torque limits. If you skip the safety shield, you are going to shatter your hardware, for sure.
But when you actually navigate those pitfalls correctly, the scale of this is staggering. This exact workflow is actively powering the most advanced robotics across multiple domains today. For legged robots, it's platforms like Isaac Lab, mixing domain randomization with that teacher/student dynamic. For autonomous driving, simulators like Carla and NVIDIA Drive Sim use massive randomization followed by real-world fine-tuning. For crazy complex things like robotic finger manipulation, projects like OpenAI's Dactyl use domain randomization at an unprecedented scale. And for industrial arms, we see a ton of system identification paired with tiny real-world adjustments. The recipe is everywhere. Fit the sim, randomize the rest, train massively, distill, and deploy safely. It's exactly what is powering the self-driving cars on your streets and the automated arms in manufacturing plants right now.
Which leaves us with a pretty profound thought to end on. We've gone from a world where teaching a robot to walk meant risking millions of dollars of shattered metal, to a world where we can run thousands of lifetimes of totally safe, simulated training in a single afternoon. As these massively parallel simulators keep getting better and begin to perfectly mirror our physical reality, will real-world trial and error for machines eventually become entirely obsolete? It's definitely something to think about as you watch the next generation of robots step out of the simulator and into our world.